A single malformed string of text brings down an entire global network. The culprit is not a random hardware glitch, but a mathematical certainty waiting for the perfect storm. In computer science, the worst-case scenario is not just bad luck. It is the absolute boundary of a system's survival, the ultimate test of its structural integrity.
To understand system stability, we must trace how we define computational work. Alan Turing conceptualized computation as discrete state changes, exposing the tension between deterministic rules and the uncertainty of whether a process will ever halt. Today, we use the random access machine model to bridge theory and engineering. However, if we ignore how data scales at the bit level, the logarithmic cost of massive numbers, our stability guarantees become nothing more than useful lies.
We categorize resource consumption using asymptotic notations. A common mistake is thinking Big O is synonymous with the worst case. In truth, Big O is just a mathematical tool, providing an upper bound for any function. The engineering contract is formed only when we apply Big O to a worst-case analysis. This intersection creates a formal guarantee that resource demand will never exceed a specific growth curve, regardless of how pathological the input becomes.
Average case analysis is mathematically elegant, but it is operationally fragile. It requires the analyst to assume a specific probability distribution for the inputs. The danger arises when the real-world data distribution diverges from the model. In high-stakes environments, data is rarely random or uniform. It is often highly structured or intentionally manipulated by adversaries. Treating this uncertainty as a predictable risk is a fatal category error.
Consider QuickSort. On average, its complexity is Big O of n log n. But if the input is already sorted and the algorithm picks the first element as a pivot, it collapses. The system moves from a logarithmic split to a quadratic nightmare. A task expected to take milliseconds suddenly takes minutes, choking the processor. This isn't an edge case. In many business applications, sorted data is actually the most common input.
Attackers actively weaponize the worst case through complexity attacks. Take regular expression denial of service. By feeding a specific string to a nested pattern, an attacker forces the engine to evaluate every possible partition and grouping of characters to find a match. This backtracking process grows exponentially. A payload of just 30 characters can freeze a server for hours, turning a tiny input into a devastating computational outage.
In aviation, the average case is legally and ethically inadmissible. Standards like DO-178C are objective-based. They mandate that the worst-case execution time be strictly bounded and verified for flight-critical software. While the standard does not mandate a specific method, allowing for either static analysis or rigorous measurement, the goal is absolute. You must prove that the system will respond within its deadline, even under maximum computational duress. Modern distributed systems ensure stability through site reliability engineering. They ignore averages and focus on tail latency, the slowest 1% of requests. Using chaos engineering, engineers intentionally crash servers and flood networks to simulate worst-case topologies. By forcing the system into these pathological states in a controlled environment, they transform theoretical fears into tested, bulletproof stability guarantees.